Hi, everyone. It's my pleasure to talk about my work with you guys. I'm Ningli Xu, a fifth-year PhD student at the Ohio State University. Rongjun Qin is my advisor. My research interest is computer vision and generative AI, with a special interest on applying generative AI on geospatial datasets, such as satellites, aerial, and street view images. Today I'm going to introduce one of our recent work on bridging the domain gap between satellite and ground view images using the power of generative model. Okay, so to begin with, this work is about given several overhead satellite images, how to generate real-world ground views. This is a very challenging problem since there is a huge domain gap between satellite and ground domains. There are huge viewing angle difference, which will introduce the distortions and occlusions. For example, satellite data observe the cities from the top-down views. It can capture the ground surface and the building roof. But for the ground view images, it observes the city in the horizontal directions, which it only mainly captures the building facade. And another difference is that the huge resolution difference. The satellite images have a resolution of 0.5 meter per pixels, but the ground view usually have a less than 5 centimeter per pixel resolution. So which makes this problem even harder. And some people may wonder why it is even a problem if there are already Google Street View data available all around the world. And I can show you that it is not the case. And there is a huge data availability imbalance between the satellite and the Google Street View data or the normal ground view data. As shown in this figure, the satellite data covers every corner of the world. It is because the collection of satellite imagery is quite easy and cheap. You just need to fly the satellite into the sky and take photos regularly. And also each satellite imagery captured a large area. In contrast, the Google Street View data only available sparsely. And the collection of Google Street View data is quite expensive and difficult because the only way to collect the data is that you drive a car or hold a 360 cameras on the street and capture the data. And also there are some places that people cannot reach to that places because the environmental reasons or the government policies. So all this factor makes the ground view data very limited. And if we take a deep look at some places, for example, so the major part of Africa, and even for the modern city like Milan in Italy is a beautiful and modern cities. There are some places that no street view data available. So this bring out our research that we want to use the existing data that both satellite and the street view data available in that areas and use the power of generative model. In our work, we use the diffusion models to bridge their domain gap and apply this model to the area that only satellite data available. Okay, so then I will show some result of the state-of-the-art methods. The first is PanelGAN, proposed in 2022. It generates the ground views based on the ground semantics. So the semantics provide the shape of the trees, the road, and the buildings, but it will not provide the details information. And we can see the synthesized results, even though it can recover the correct shape of the buildings and the roads, but it produces blurry and artifacts results. And the other work is set to density, proposed in 2023. It performed the ground view generation based on the estimated density map estimated from the satellite. And for this result, it cannot even recover the correct building shape. it because the geometry is in a poor quality. And so then I will introduce our method. The key observation of our method is that instead of using the semantics or the geometry of the satellite, we fully utilize the weak facade information from the satellite. Because even so, the building is observed by the satellite from the top-down view, but the satellite data can still capture the weak facade information, which can provide a valuable cues for our diffusion model to generate the ground views. And based on that, we apply our diffusion model condition on the ground view satellite textures with depths embedded into that. And compared to the ground truth data, we can see our results not only recover the realistic views, but also capture the correct building shape and even the facade details like the number of storage and the textures. And then I will introduce the pipeline of our method. Our pipeline starts from a set of satellite images. We then generate the raw 3D geometry using the traditional dense matching method. But this raw geometry contains a lot of noisy and uncertainty, especially with the building facade surface. We then introduce a refinement module to refine the geometries so that we can better project the satellite texture from the top-down view to the ground view as the condition. We further extract the high-frequency age map from these textures, and we take these two conditions, sent to the two encoders to extract the high-level scene layout and appearance information to guide the diffusion models, which in our case is Stable Diffusion version 1.5. And in addition, we also introduce geolocation priori to better help the diffusion model to synthesize the style of that location. And yeah, that's pretty much the pipeline of our method. And I will introduce each component later. And the first component, which is very important, is to refine the raw satellite geometries. As you can see from the left images, it contains a lot of noises, especially around the building facade surface. This one. So this even facade surface will distort the facade textures, which makes this can hardly be used as a condition for diffusion to generate the ground views. And what we do is that we first apply a UNet to predict the building pixels and the ground pixels with a binary segmentation task. And we further to rectify the building boundary to make the boundary as straight as possible. And then based on these building regions, we flatten the ground pixels to make the ground, especially the building facade surface, smooth and even. And you can see that the building facade looks like more regular. And here we provide more refinement results. We can see that after the refinement, the building facade details like the windows or the floors looks more regular than before. And once we got the refined satellite geometries, we can send this into the encoders to extract the high-level scene layout informations, which basically is based on the control net that takes the left low-resolution texture as an input, extract the feature, and combine that feature into the diffusion models to generate the high-resolution ground view images. And the key point of this process is that we can see that our method can bridge more than 10 times resolution difference, yeah, which is quite amazing. And the third component is that we introduce the geolocation priori. which adds a few additional learnable parameters inside the diffusion models, which is the theta, to let the diffusion model to quickly learn the style of the scenes. And since the training of the geolocation priorities requires less memory and computation resources compared to training the whole diffusion models. And here we show some example to demonstrate the effectiveness of the geolocation priori. We first show a comparison between the generated result with and without geolocation priori. If without this prioris, we can see that the diffusion model struggles with synthesize the ground view that's similar to the ground truth. Even after the training step of 44,000, it still cannot perfectly to reconstruct the ground truth. And if with our geolocation priori, even with the 2000 training step, the diffusion model can quickly to generate the pretty good ground views. And as the training step increase, the result becomes even better. And the other example is that given the same conditions as shown in this ones, we can train different geolocation priori that represent different cities or different locations. For example, we can generate the Hong Kong, Dubai, London, and the good point is that training of this geolocation priori for each location only requires less than 100 images, and the training time should be less than 30 minutes. And so in that ways, our encoders serves like extract the high level structures like the building shape, the road shape, and a little bit weak facade layout. And the geolocation priori serves like add more geospecific details based on that. And now I'm going to introduce the dataset I use. And we are going to publish this dataset. It is based on open public satellite dataset called DFC 2019. The main feature of this dataset is that it provides accurately aligned satellite and ground view images, as shown in these figures. And it requires a georeference process to align the satellite and the ground view data in the same coordinate system. It contains more than 4,000 pairs, and so this dataset enables the training of our texture-guided generation components. And then I will show some experiment results. To begin with, here are the qualitative results of the state-of-the-art method and ours. We can take a deep look at these examples. We can say that the cross MLP and panel GAN can reconstruct the rough building shape, but it is not realistic and a lot of blurry and artifact. But ours can generate a more realistic and a more similar result than the ground truth. And here we provide more qualitative results of our methods on more location. I would say that our method can better recover the buildings and the road. All these are big or large structures. And for the small object or small structure, such as the cars, the pedestrian or traffic lights, we are struggle with reconstructing this small object. Yeah, as you can see that the bottom examples, so the cars, we cannot reconstruct it well. And to demonstrate the generalizability of our method, we also perform cross-location validation experiment. We train our model on Jacksonville, Florida, and directly test on the Omaha, Nebraska, which is more than 1,000 kilometers away. And here is the results. We can see that our methods still produce better realistic ground views than the baselines. And also same for the building facade. But we can also notice that there are some examples that ours tend to produce some random texture, such as these examples. And here we show the quantitative evaluation of ours and the baseline methods. The evaluation was performed in 4 levels matrix. Ours achieved the best performance on 3 of them, except the low level matrix. Yes, for example, the semantic level matrix is to compute in the generated images how many building pixels are correctly reconstructed, how many ground pixels or sky pixels are correctly reconstructed. Also for the perception level like FID or dream scene. So all these methods is based on a large vision foundation models that training on a large realistic data sets. So this foundation model have the same like human perception ability to perceive these images. So to calculate the difference in the perception levels, we use this foundation model to extract the feature from both the generated images and the ground truth images and compare the difference in the features. And this matrix only focus on the high level features, not on the low level like per pixel difference. And for the low level like PSNR or SSM, this matrix more focus on the per pixel difference, which is not so necessary in our case, because even so we reconstruct a correct building shape and with the correct facade layout, but the lighting condition, the shadow conditions, all these factors will highly impact the low level matrix. So we care more about the perception level. And even so our method can already generate the realistic ground views, there are still some limitations on our methods. The first limitation is that ours sometimes fail to reconstruct the small object. In this case, the bridge in the satellite view cannot constructed by our methods. Yes, in our result, the bridge is missing. This is because the bridge only have a width in 5 to 10 pixels in the satellite images, which is quite small. And our geometry reconstruction method can hardly to reconstruct the bridge or other small object. Yeah, so the same thing for the traffic light, cars or pedestrian. And another limitation is that there's no consistency across the neighboring ground views. This example shows that the 2 neighboring views only have 10 meters distance between each others, and ours results cannot reconstruct the consistent buildings across these 2 views. We can see that the orange rectangles corresponding to the same buildings, but our result cannot reconstruct the same number of floors or the same appearance. And this is because the randomness property of the diffusion models, every time the diffusion model will generate a slightly different result, which makes the neighboring views not consistent. And this is also very important if we show people the result that the 2 neighboring views are not consistency, the people will not regard this as a good method. So this is also our future research direction, that to add some constraint on the across the neighboring views to produce the multi-view consistent ground view images. And to recap, we proposed a novel diffusion-based pipeline to perform ground view generation from satellite images. And our geometry refinement module can effectively correct the distortion of satellite textures. And our texture-guided generation components can bridge over 10 times resolution difference between satellite and ground views. And yeah, in the end, I would also like to thank our sponsor and my advisor to support my research work. Yeah, thank you. Yeah, if you have some problems, please let me know.
All right, fantastic. Well, it does look like we do have a few questions queued up in the Q&A widget. So if you want to head over there and take a look at those questions.
Okay. Okay. So yeah, for the first questions that David proposed, how does your method handle overhanging structures with shaded or areas hidden from the overhead satellite? I would say that our method cannot handle these structures, and we only focus on the in the urban areas with some buildings. Yeah. And can you system integrate together system satellite views that are taken from different viewing angles? If I understand correctly, you mean that the satellite views not only from the top-down view, but also from the oblique views? I think our system can handle that. We basically to project the satellite from multi-views onto the geometry. So yeah, we can handle that. And how does the Google Earth create its 3D models? I think I cannot answer that questions. You can ask Google Earth team. Yeah, but I can guess that they probably use some learning-based method to estimate the geometry from the maybe from the lidar or from the aerial images. Yeah. And besides DFC, what other data I use? I think we did ground level Google Street. Yeah, that's a good question. And the DFC only provides the satellite images, and we basically to collect the ground level data by ourselves. We download from the Google Street View API, and using our own georeference techniques to georeference the both data into the same coordinate system. And for the open source ground level imagery, I think we cannot directly use the Google Street View images, but instead there is a open source website called Mapillary. I can post the link later. This website provides the open source the ground view images. Yeah. And does your method only works on specific fixed viewports? I think so. In our case, the ground view is in a panorama format, which people stand on the street and it can have a 360 field of view, so that there is no fixed viewports.